You know when you're talking to ChatGPT or Gemini or Claude, it feels like actual magic, right? Like you're communicating with a real thinking being. But here's the thing, it's not magic. It's this incredible, massive feat of engineering. So let's pull back the curtain and actually unpack how these things are built from the ground up. So let's get right down to it. The most fundamental question is this: how does a chatbot even know what to write next? When you type something in, what's the process for it picking the very next word? And then the one after that, and the one after that. The basic idea, well, it's actually pretty simple. But how they pull it off? Oh, that's where it gets mind-bendingly complex. Believe it or not, it all comes down to a really, really sophisticated prediction game. That's it. At its heart, an LLM isn't trying to understand things the way we do. Its one and only job is to guess, with incredible accuracy, the most likely next word in any given sentence. Everything else you see, the poetry, the code, the explanations of quantum physics, that all just emerges from this one simple, powerful skill. Right, so this whole next word prediction game, that's the key. It's the absolute foundation for everything that follows. Seriously, if you can wrap your head around this one idea, you're already most of the way there. So, okay, here's the slightly more technical way to think about it. An LLM is basically a giant mathematical function. You feed it some text and it gives you back a massive list of all the possible words that could come next. But, and this is important, it doesn't just pick one. It assigns a probability to every single word. So it's not thinking the next word is the. It's thinking, well, there's a 40% chance it's the, maybe a 10% chance it's and on for thousands of words. Then it kind of rolls the dice based on those odds. And that little bit of randomness, that's exactly why you can ask the same question twice and get a totally different but still valid answer. Okay, so how in the world does a machine get that good at predicting human language? Well, like any good student, it needs to study. And I mean, it needs to study a lot. So let's talk about the raw ingredients, the data. And just a heads up, the scale here is going to be hard to even imagine. Just to try and put this into perspective, let's take GPT-3, which is an older model at this point. If you were to sit down and read all the text it was trained on, and I mean reading 24/7, no breaks, it would take you more than 2,600 years. Just let that sink in. It's an absolutely mind-boggling amount of information. And guess what? The models have only gotten bigger since then. A lot bigger. The latest ones are trained on something like 70 trillion tokens. Now, a token is basically just a word or sometimes a piece of a word. So yeah, we are talking about a data set that contains a huge slice of the internet, a massive library of books, all of Wikipedia, source code from places like GitHub, the whole shebang. And as you can probably guess, sifting through all that data costs a fortune. We're not talking about a few powerful computers here, just the raw compute cost, paying for thousands and thousands of specialized computer chips to run nonstop for months to train something like GPT-4, that alone was over $100 million. And that's before you even pay the army of brilliant engineers and researchers who build it. But here's a crucial point. You can't just hoover up the entire internet and feed it to the model, warts and all. There's an old saying in computer science that is the absolute gospel here. Garbage in, garbage out. The model is only ever going to be as good as the data you train it on. So, that enormous mountain of text, it has to be cleaned meticulously. And this cleaning process, it's a monumental job in itself. First up, filtering. You got to get rid of all the junk, the HTML tags, the website ads, just the low-quality spammy text. Then there's deduplication. Think about it. The same news article can be copied and pasted on thousands of different websites, so they have to find and remove all the identical copies, the near copies, even stuff that's just reworded. And then, maybe most importantly, they de-identify the data, stripping out any personally identifiable information to protect people's privacy.
All right, so the data is clean, but there's one last prep step. Computers, they don't speak English, they speak math, they need numbers. So this process called tokenization chops up all that text into those little pieces we talked about, the tokens. Then it turns each token into a long list of numbers, a vector. But here's the genius part. These numbers aren't random. This list of numbers, they call it an embedding, actually captures the meaning of the word. So words with similar meanings like king and queen or walking and running will have very similar lists of numbers. It's like turning language into a giant map of meaning, all with pure math.
Okay, so we've got our fuel. this massive, clean, number-based data set. Now we need the engine. And this is where the real revolution in AI happened. We're talking about the invention of a new kind of architecture that could finally make sense of all this data and understand context on a whole new level. That engine is called the transformer, and you really can't overstate how important this was. Before the transformer came along in 2017, AI models read text kind of like we do, one word at a time, in order. The problem is, they'd easily forget what was said at the beginning of a long paragraph. The transformer completely changed the game. Why? Because it was designed to look at all the words in a sentence or a paragraph at the exact same time. It sees the whole picture at once. And the secret sauce inside the transformer is this brilliant mechanism called attention. The best way to think about it is that it lets every single word talk to every other word in the text. So the model sees the word bank. By itself, that could mean a riverbank or a financial bank, right? The attention mechanism lets the word bank look around and see its neighbors. If it sees river and water, it knows, I'm a riverbank. If it sees money and account, it thinks, okay, I'm a financial bank. It's how context is built mathematically. So how does the model actually learn during training? Well, it's all about tuning its parameters. Imagine a machine with billions or even trillions of tiny knobs and dials. A parameter is just one of those dials. The whole training process is just the model automatically tweaking every single one of those dials over and over, trying to find the perfect setting to get better and better at that next word prediction game. And the number of dials we're talking about, it's just wild. GPT-4 is estimated to have 1.76 trillion of them. Now, think about that. You're trying to tune 1.76 trillion knobs using 70 trillion pieces of text as your guide. The amount of computing power you need for that is almost beyond comprehension. We're talking about huge, custom-built data centers, packed with thousands and thousands of those specialized GPU chips you hear about from companies like NVIDIA. These giant computer farms run at full blast 24/7 for months just to get through one single training session. It's a truly monumental undertaking. Okay, so after all of that, what do we have? We have an amazing text predictor. Some people call it a stochastic parrot. It's brilliant at mimicking human language patterns, it knows facts, it knows grammar, but it's not an assistant. It doesn't know how to follow instructions or have a helpful conversation. To get that, we need a whole separate and super important second phase of training. So let's just make the distinction really clear. That first big phase, that's called pre-training. Think of that as the model going to the world's biggest library and reading every single book. It's just absorbing information. The second phase is fine-tuning. This is more like sending the model to finishing school. It's not about learning new facts, it's about learning manners, how to answer questions helpfully, how to follow instructions. And for this, you don't use the whole internet. You use much smaller, super high-quality, human-created datasets. And a huge part of that finishing school is a technique called reinforcement learning with human feedback, or RLHF for short. It's pretty cool how it works. The model is given a prompt, and it writes, say, 3 different answers. Then a real human looks at those 3 answers and ranks them. This one's the best, this one's okay, this one's bad. That feedback then goes back into the model, and it learns. It's basically a giant feedback loop that teaches the AI what we, as humans, actually find helpful and safe. This is the secret to making a chatbot that's not just a know-it-all, but is actually useful and aligned with our values. All right, so the model's been built, it's been fine-tuned, it's ready. But how do we know if it's actually any good? How do you grade a student that gives a slightly different, creative answer every single time you ask it a question? This is the final and really tricky part of the whole process, evaluation. Because there's not just one right answer. The evaluators have to get really creative. One thing they do is measure semantic similarity. Basically, they check if the model's answer means the same thing as the target answer, even if the words are different. They also do what you might expect. They make it take tests, real tests, designed for smart humans. We're talking tough math competitions, complex coding challenges, even things like the bar exam or medical licensing exams. And here's a wild twist. One of the best ways to grade a new AI is to have another, even more powerful AI act as the judge. It's like AI on AI evaluation. So after this entire process, you're left with something pretty profound. The most incredible abilities these models have, their ability to reason, to be creative, none of that was explicitly programmed in by a human. It all just emerges from the mind-boggling scale and complexity. In fact, even the creators will tell you they don't fully understand why the model makes the exact choices it does. This intelligence isn't designed. It's an emergent property of the whole system. And that really leaves us with a huge, fascinating question to chew on, doesn't it? We figured out how to build a system that can learn from a staggering amount of information. But if the end result is a form of reasoning that emerges in ways we can't fully predict or explain, then what have we actually created? And what does that mean for all of us as we start to use this technology more and more every day?